So we've now seen that the upper Riemann sums do indeed get indefinitely close to this value x from above. What I now want to show is that the lower Riemann sums get indefinitely close to this value x from below. And this will help to cement the proof idea in your head because it's pretty much exactly the same proof idea, just kind of the mirror image of it. So we want to show that the lower Riemann sums get indefinitely close to the value x, this time from below. So once again, we will let epsilon be greater than 0, and this time we're going to consider the interval going to the left of x, not going to the right. So instead we'll be looking at the point x minus epsilon here, and we want to show that we can find a lower Riemann sum that is going to be inside this interval x minus epsilon, not including x minus epsilon, up to x. And if I can do this for all epsilon greater than 0, then that will capture the concept that we have lower Riemann sums getting indefinitely close to this value x from below. So how am I going to do this? Well, once again, I'm going to find lower Riemann sums just over the two subintervals that are within epsilon over 2 distance below the values of x1 and x2 that make up x. So let's do this firstly for the interval AB. So here is the value x1 once again on the number line, and then we'll consider this interval from x1 minus epsilon over 2, not including that value, to, 2 should be to x1, and including x1. And now my claim is that I can find you a lower Riemann sum just over the interval AB such that it is inside this interval, i.e. strictly greater than this and less than or equal to x1. So on the picture we'll mark it here, and we'll call that lower Riemann sum the lower Riemann sum, and we'll say over dissection d1 of f. And again, the dissection d1 is just a dissection of the interval AB. Now why can I do that? Well, of course it's going to be less than or equal to x1 because all of the lower Riemann sums are less than or equal to the value of the actual integral, because it is the supremum of the lower Riemann sums, so it's an upper bound for them. Now why is it true that I can always find one that is strictly greater than x1 minus epsilon over 2? Because if I couldn't, then x1 minus epsilon over 2 would be an upper bound for the lower Riemann sums. If there was not one that was strictly greater than it, then it would be the case that they were all less than or equal to it, and hence it would satisfy the definition of an upper bound, but that would be in contradiction to x1 being the least upper bound, because this one is less than x1 and it would be an upper bound, so it would be a better candidate for the least upper bound. So that's why it can't be the case that all of them are less than or equal to this. There must be one that is strictly greater than it. So here it is, the lower Riemann sum over the dissection d1 of f, and it is inside this interval from x1 minus epsilon over 2 to x1. Similarly, for x2 the exact same argument holds true. Here is x2, consider the interval from x2 minus epsilon over 2 to x2, and again for the exact same reasons I can find you a lower Riemann sum, and we'll say we'll call it dissection 2 again, of f, that is inside that interval, i.e. strictly greater than x2 minus epsilon over 2, but less than or equal to the value of x2. And that dissection d2 will be a dissection just of the interval bc. Now what I can do, just as I did in the case of the upper Riemann sum argument, is create the combined dissection. So d bar, which is a combined dissection of the entire interval AC, and it's made by just taking all the cuts of d1 and all the cuts of d2 and making them into a dissection of the overall interval AC. Then what I can consider is the lower Riemann sum over d bar of the function f, which is now a lower Riemann sum over my entire interval AC, and of course again that is just going to be equal to the sum of these two lower Riemann sums. So it'll be the lower Riemann sum of f over d1 plus the lower Riemann sum of f over d2. And I'll just draw a picture again to convince you of that. So if here is my interval AC, here is AB, and then we've got the dissection D1, which we'll show in green. We just have a few points just for simplicity, and the dissection D2, that's just, again, for simplicity, we might just have one cut in D2. So here are these two separate dissections. The overall thing makes the entire dissection, so this, are the cuts for the entire dissection D bar. And then if you think about trying to construct this lower Riemann sum for the function over D bar, you take the length of this subinterval here, multiply it by the infimum of the function over that. You then take the length of this interval here, multiply it by the infimum of the function over that interval. The length of this interval here, multiply it by the infimum of the function over that interval. Now note, the infimum of the function doesn't change just because we're now taking the lower Riemann sum over this entire interval rather than just the interval AB. So actually that calculation that we've just done there, we've taken all these lengths and multiplied them by their respective infima. That's the exact same calculation that you would have performed here when you were just taking a lower Riemann sum over the interval AB. So this bit remains exactly the same. It's just now that we have to continue on to these intervals here, which come from this bit. So you take the length of this, times it by its infimum, length of this, times it by its infimum. Again, that's the exact same calculation as you would have done here when you were just taking the lower Riemann sum over this subinterval, BC. So we're going to do that exact same calculation. It doesn't matter that we've done all of this bit in front. We just now add the two together, and that will make the overall lower Riemann sum that you have to do for the entire interval AC over that dissection D bar that is found by the combining of the dissections D1 and D2. So that's excellent. And now my claim is that if these two were found in this way so that they are inside these intervals, then this one, which is a dissection, well, it's a lower Riemann sum over a dissection of the entire interval AC, is guaranteed to be in my desired interval. So again, the argument for that is very simple. So the maximum value that this lower Riemann sum can have is obviously going to be x1 plus x2, because this is the maximum value of this is the maximum value of this. So the biggest value it can take on is x1 plus x2, which is of course just x. And then this one we know is strictly greater than this. This one we know is strictly greater than this. So the sum of them is going to be strictly greater than these two sums, which is x1 plus x2, which is x, plus minus 2 lots of epsilon over 2, which is just minus epsilon. So it's going to be strictly greater than x minus epsilon, and therefore it's going to be inside this interval x minus epsilon 2x. Hence, we have found a dissection that is inside that interval. So whatever epsilon you give me, this argument holds true. I just have to take epsilon over 2 and find these lower Riemann sums in this way, which you can always do for the arguments that I've given you, and then from them you're able to construct a lower Riemann sum over the entire interval that is guaranteed to be within this interval. And because this holds true for any epsilon greater than 0, that means that there truly are lower Riemann sums getting indefinitely close to this value x from below. So we have now completed our proof of part 1 of the additivity property, because we've shown that for this value x, which is the sum of the two integrals, that there are upper Riemann sums that get indefinitely close to that value from above, and there are lower Riemann sums that get indefinitely close to it from below. And by the argument that we gave in part 1, that suffices to prove that the infimum of the upper Riemann sums is equal to the supremum of the lower Riemann sums, and that the value of those two things is equal to this value x, i.e. this. So what have we overall shown then? We have shown that if our function is Riemann integrable over the interval AB and it's Riemann integrable over the interval BC, then it is Riemann integrable over the entire interval AC, and that the value of that integral is the sum of the integrals over the two distinct subintervals.